Algebra 1, Unit 1, Expressions, Equations and Functions. Today we are going to see the last lesson in this chapter, representing relations and functions. After completing this lesson, you will be able to represent functions as rules, tables, and graphs. Relations. We know many relations. Many things are related to each other. In this picture, there is a relation between teacher and students. We have relationship with God, parents and their children. Of course, there is a relation. Relationships are everywhere. For example, schools, principals. Every school generally has a principal or head of the school. Countries, presidents. Each country has a president or prime minister. There is a relation. Houses and landlords. Things and their price. Human, food. We can see relations everywhere. Here in set A, John and Sophie, for example, they are parents. In set B, we have Xenia, Emily, and David, or the children. They may be related this way. We can map them. So we can call it relation. A relation is a mapping or pairing of input values with output values. The set of input values is the domain, and the set of output values is the range. Here there is a relation. That's why we are writing R in between the two sets. Now we will see how to represent relations. A relation can be represented in the following ways. We may represent relation using order pairs or table. We use graphs to represent relations or functions. And we also use mapping to represent relations. Now let us see some more relations. The total cost of pens depends on number of pens. Similarly, the total cost of ice creams depends upon number of ice creams. There is a relation between the total cost of toys and the number of toys. The total cost of pens or ice creams or books is a function of their number. Similarly, in math, we have many different functions. Let us see an example. Set A, we have three elements, 1, 2, 3. And in set B, we have three other elements, 1, 4, and 9. They are related, 1, 1, 2, 4, and 3, 9. How are they related? You may guess it. Clearly we can see 1 square equals to 1, 2 squared equals 4, and 3 squared equals 9. Therefore, the function is x squared equals y, or y is x squared. A function is a relation for which each input has exactly one output. In this example, the inputs 1, 2, and 3 have outputs 1, 4, and 9. If any input of a relation has more than one output, then the relation is not a function. For example, here 3 squared is 9. Therefore, 3 is mapped with 9. If we map 3 with 4 and 9, obviously it is not correct. Therefore, it is not a function. As we have seen before, the elements in the first set is domain and the elements in the second set is the range. We also call elements in the first set as x coordinates and elements in the second set are y coordinates. Elements in the domain are independent variables and elements in the range are dependent variables. Let us see another example. Let function f of x equals 2x plus 3. Now we will take different input values and we will find output values, and then we draw a mapping diagram for this function. We also use order pairs to represent the same functions. We have learned how to evaluate expressions in the first lesson. We use the same method to find outputs. When x is 0, f of 0 equals 2 times 0 plus 3, which is 3. Simply replace x with the x value 0. Now we have output 3. Write this as an order pair 0 and 3. When x is 1, f of 1 equals 5. When x is 2, we have output 7. And finally, we will take x as negative 3. Then we get output negative 3. Here, inputs or x values or domain is 0, 1, 2, and negative 3. These are independent variables. And output range or y values are 3, 5, 7, and negative 3. These are dependent variables. Now we can represent this function as a set of order pairs. F is 0, 3, 1, 5, 2, 7, and negative 3, negative 3. We can represent this function as an order pair. Now we will represent this function as a mapping diagram. In set A or in domain, we have 0, 1, 2, and negative 3. And in range, we have 3, 5, 7, and negative 3. Now we map them. A relation or function can be represented as a set of order pairs or as an equation. The relation or function is then the set of all order pairs xy that makes the equation true. Now we will see whether these relations are functions. In the previous example, we have taken this function f of x equals 2x plus 3 is also can be represented as set of order pairs. What about this? F is 0, 3, 0, 5, 2, 7, negative 3, negative 3. Is this a function? No. When you see the order pairs, make sure the x values are not repeated. If x values are repeated, then that relation is not a function. We'll see one more example. Is it a function? We have 0, 3, 1, 5, 1, 7, negative 3, negative 3. Clearly, this is not a function because the x coordinate 1 is repeated. We will see the mapping diagrams. Is it a function? No, it is not, because the input 1 has two different outputs, which is not possible. What about this? The input 0 has two outputs 3 and 5, again, which is not possible. Therefore, this is also not a function. How do you check whether the given graphs are functions? We have a vertical line test. If no vertical line intersects a graph in more than one point, the graph represents a function. In the first example, the vertical line intersects the graph at only one point. Therefore, this graph is a function. If vertical line intersects the graph in two or more points, then the graph does not represent a function. In the second example, the vertical line in red intersects the graph in blue in 2 points. Therefore, this is not a function. A function consists of two sets. Domain is a set of inputs and the range is set of outputs. A pairing of inputs with outputs such that each input is paired with exactly one output. The input variable is called an independent variable and the output is called dependent variable. In one function, each element of domain pairs to exactly one unique element of the range. In onto function, each element of the range also corresponds to an element of the domain. If the function is both one and onto, we call one onto function. Based on whether the graph is continuous or not, we have two types of functions, or discrete and continuous functions. The graph of discrete function consists of separate points, and the graph of continuous function is unbroken. Example 1. Identify the domain and range of a function. In this example, clearly the input values are 1.5, 2.3, 3.1, and 4.2. And the range or output values are 7.8, 11.96, 16.12, and 21.82. One more example. Identify domain and range. Domain is the input values 1, 2, 3, 4, and range 1, 8, 27, and 64. Now let us represent a function using a table, graph, mapping diagram, and a rule. The function f of x equals 4 minus 2x. This function is a continuous function, therefore the domain is all reals. Let us take domain 1, 2, 3, and 4. Therefore, we'll get corresponding values of range 2, 0, -2, -4. We can write domain and range in a table like this. We also can represent function as a mapping diagram. We take the first set 1, 2, 3, 4 and the range 2, 0, -2, and -4 and map them. We have this table. We can write order pairs from this table 1, 2, 2, 0, 3, -2, and 4, -4. And now we will draw x-axis and y-axis and plot these points 1, 2, 2, 0, 3, -2, and 4, -4. This is how we will represent the function as a graph. We may join these points to see whether the graph is continuous or not. Obviously, this gives a straight line and it is a continuous function. Y equals 4 minus 2x. Congratulations! Now we have completed this lesson. You have learned how to represent a function as a rule, table, and a graph. This is the end of the first chapter.